Yeah, I go with cloud. I think you should go local first, and then I go.
Yeah.
Okay.
Perfect. All right. Hello, everyone. Welcome back to, I think this is week 4 now. So thank you for coming back. And today we have the pleasure to have Dr. Manizheh Ghaemi to introduce us to convolutional neural networks. I'll first introduce Manizheh. So she is a postdoc fellow at University of Calgary. She has obtained her PhD in software engineering, intelligent system, and robotics. And her main field of interest is optimization in AI and machine learning algorithms. She also has experience in applying machine learning for high dimensional data and also introducing algorithms suitable for such kind of data. Also, she has approached optimization in robotic problems, including robot localization problem. So please go ahead and take it away. I think you have some PowerPoint slides first, and then we'll go through the Google Colab, and I will share the documents in the Google Drive with everyone. Please go ahead. Thank you very much.
Hello, everyone, and thank you for the introduction. Yes, we will today we will just have some introductions to convolutional neural networks, or CNN. I will go through some first definitions, then we will jump into coding. Let me just share my screen. Okay. Yeah. You have my screen now?
Yep.
Okay, nice. Oh yeah, we will go through some to introduce something about convolutional neural networks, or CNN in short, and we will do classifications for that. I have just provided a picture here. You can see if you just compare the picture from right to left, you can see how what is the resolution in these pictures. It means that if the resolution is high, we have lots of pixels. So processing will get some very huge time. And also, when you just look at the picture, it is said that 90% of our mind energy is just consumed for visual processing. So our mission is to inspire how our brain works and just follow those processes as far as we can, and introduce some productable algorithms to do image processing or for other tasks too. So CNN is just maybe a very start algorithm to work in this regard. I mean, CNN is based on what is our main is doing when it sees a picture. So I hope you already have some idea about what is artificial neural networks is. CNN is a subtype of artificial neural networks, or ANN. And it is widely used for image, speech, and audio signal processing. To better say, it's a kind of deep learning algorithm. You might have heard a lot about deep learning algorithms, and they have been popular most recently. And there was a huge progress in this regard. CNN is popular for this kind of data like image and speech because they can handle high dimensional data very well. So As I said, we want to follow how our brain functions when it sees a picture. For example, if you see a bicycle, you automatically divide it into sub images. Your mind does that, of course. Your mind divides it into some sub images, analyze them, and then assemble sub images, and then says that, oh, it is a bicycle, but you never know what's going on your mind. So we will CNN does the same. To just give you a clue, what is the difference between an ANN or artificial neural network and CNN? I will just give you an example. In this slide on the left lower side, you can see a simple neural network. And in the right side, you can see architecture of a CNN. Imagine that you have a photo which is which the size is 300 by 300, and because it is a colored image, it has three channels. So the dimension, if you just want to feed it into a neural network, the dimension should be 300 by 300 by 3, and this is a huge number. For example, imagine, okay, we say that, okay, it is not that big, but imagine we are going to have multiple layers in ANN, and in the following layers, we will just have, we will just multiply each pixel, each data by a weight, and we will have huge number of neurons. So if we just go through processing this image, if we want to just classify an image with simple artificial neural networks, we will have huge number of parameters to handle. But CNN wants to just escape that process and just reduce the size of the photo or images to just better process it. I assume that you have an idea why what we do mean by classification. But I will say some just definition. By classification, we mean that, for example, for so many years, you have seen lots of, for example, cops, and just at the first glance, you can understand what the cop looks like. So how did you learn that? You just saw some samples of cops and then know, okay, what this is what a cop looks like. So when you just, but it is not, it doesn't mean that you have learned for any type of cop, any size. You just have the pattern. And this is the classification. But here with CNN, as I said, CNN is a layered architecture. I mean that we will have we will get the input, which is image in our workshop, and we will have some layers of calculations, some layers that our image will go through, and at last, as an output, we want to say that, okay, this is a cup, or this is an animal, or this is a flower. But to better say that, we know what is our input, and we know what is the output. And in between the input layer and the output layer, we have some layers. By layers, I mean that we have some stages of calculations. We have some functions, which is just applied on our input data. But for some years, there was a saying that, okay, we have the input, we multiply it with some weights or with some values, and at the last, we just reach some result. But how we can just adjust those weights, how we can say that, okay, we should multiply this image at the first layer with this value, at the next layer with this value, how we can choose those values. There are some strategies for that. For example, if we want to just extract the edges in the image, for example, in our mind, if it wants to just understand what is, for example, a flower is, it automatically detects the edges. It just have the idea how to distinguish a flower from its environment. So we have a special filter, let's say, or a special matrix, or a special kind of weights to calculate the edges. But later, at later layers of calculations, we don't really understand what is going on. So we can say that we should do something. We should just learn how to get those values. And this is what learning means. We are going to understand how we can get those values. We want to learn those values because we have the input, we know the output, but we should learn the layers. And CNN, that is our subject today. In the first layers, it just understands some basic ideas like what is the edges, what is the color. But at later layers, it can understand, okay, for example, for this animal, it will know that, okay, this is the head of this bird, this is the body of it, and something like that. And then it assembles that and then understands that, okay, this is the whole animal, and I can say that, okay, yeah, this is animal, it is not a flower. I'm just going through some let's say some brief description of what each layer does, but let me just go back and have a look at this photo. Look by in the right bottom side, the convolutional network. By layer, I mean this. We have the input. For example, here is a digit 2, which is handwritten 2, and at the next stages, from left to right, we have some layers. We have some computations. So CNN has 3 computational components. We have convolutional layer, pooling layers, and fully connected layers. And we will apply these layers on the input layer by layer to just understand, just to how to classify an image. Okay, let's see what each layer does. Okay, the first layer is just, okay, sorry. The first layer is our convolutional layer. Let's say that convolutional layer is the just we can say that most of the computations is done there. As I said, we have the input, we multiply it by some values. The multiplications is done in this layer, so the majority of the computation is done here. And I have provided here just a mathematic matrix and filters that will go through the input layer. Let's say that we have a photo, it is one channel, so we have values between 0 and 255. The higher the number, the brighter the value. So in this matrix, if you can see 10 as a value, or a 0, you can see that, okay, this is a gray, this is a photo where the 10s are just brighter than 0 values. But for example, if imagine that we want to just detect the edges, even when you look at this matrix, you see that, okay, there is a difference in the middle of the matrix. I mean, from 10 to 0, there's a change in the values, so that there must be a edge there. To just get that idea, you will see that we have a 3 by 3 matrix here, which is 1 at the left, 0 at the center, and -1 at the right side. And the mission of this matrix is that it will go through this input matrix. It will be multiplied by it, just cell by cell, and then it will be just sum the values. For example, we will multiply 1 by 10 plus 0 by this 10, then -1 by the third 10, and so on. And we will just sum up them, and we will reach to a value. Then we will just move this filter, which is in the middle, one, or let's say for now, let's say that we will move it just 1 cell each time. We will move it to the right. Then, so our next block for processing will be this block, which is 2 columns of 10 and 1 column 0. And we will do the same until we reach to the just the right side of the this matrix. Then we will just move it down and continue this process until we get some values, which you can see at the right side. Just let me. Okay. But as I said, you will just go through this process. If you have just one channel, this filter will be applied on one channel. But if you have 3 channels for colored images, which you should go through each and every channel and do these calculations there. So this is what is done in our convolutional layers. We will see when we just go through coding, we will see some activation functions. You may have heard about this when you were maybe you were in introductions about ANN, artificial neural networks, but here are just funny showing of activation functions. But the most famous one is this one, the ReLU one. It is really simple. It's just whatever it gets, it just checks if it is more than 0 or less than 0. And it just adds some non-linearities to the input. I will not go deeply to the details, but this is what activation functions does. It just introduces some non-linearities. You know that we have in CNN, like in ANN, we have some forward steps and backward steps. Okay, we said that we give feed the input to the layer, and to the network, and then we have the output. But at first, for example, we were not sure about what is the values for the filters. But anyway, we choose some values, we get an output, but it will be different from the actual output. So we will just during the forward stage, let's say, we will see we will get some values, but we will get some errors. We need to go backward and just correct our initial guesses. That is what learning means. And these functions will be used in our stages to just calculate or correct our initial guesses. And the next, let's say, layer is the pooling layer, or you may see in some references it is called downsampling layer. When we just go to the coding, we will see them as n dot max pooling or average pooling, or something in coding, but let's keep it there. But what is done in pooling layer? Okay, we said that in convolutional layer, we do just multiply our input with some filter. Okay, now what is pooling layer does is to reduce the dimensionality of the input. At the very beginning, we told that the problem with image processing, for example, is that we have a huge number of parameters to handle. So CNN, the basic idea of CNN is to reduce that size, and this is done mainly in the pooling layer. You remember that in our convolutional layer, which was here, finally we reach to another matrix. This matrix also has a smaller dimension than the initial one, but it's still pooling layer is just reducing its dimensionality too. We can just choose between two options. We can make, for example, we have the matrix that is the output of our convolutional layer. We can just pick the maximum, or we can average the values of that matrix. Each of these have its own pros and cons. For example, if we just get the maximum, so we are just neglecting the other values. But if we just do the average, we are also losing some information. But that is, we should just sacrifice something to get to reduce the size of our photo. But the difference between pooling layer and our convolutional layer is that here we just take the maximum value or the average value, and we are not going through some multiplication, some values, some weights, let's say. We don't have those. We are just averaging or just get the maximum values. And as I said, we do have some information loss, but from the other side, it reduces complexity, and it helps us to just avoid overfitting. I won't say lots of details about these things, but I want you to just get the whole idea of what CNN does and its difference between simple A and N. And okay, I just bring our initial image that you saw at the very first slides here too. Okay, look at this photo. We have the handwritten digit, which you can easily understand. It is digit 2, but we just go through some layers, which you can see there, convolutional layer, pooling layers. But at the end, we have another layer, which is fully connected layer. This layer is just at the very end of the our convolutional and pooling layers. We just flatten our, let's say, flatten our layers and feed those matrices to a very simple ANN, but the difference is that the size here is much smaller than when we just have ANN from the beginning. So let's say another way. For example, we have input digit 2. We have some convolutional layers. For example, at the very left side, we have 20. Sorry, we have N1, like for example, 32 channels. Then we have some other layers. For example, say we have 64 channels. And it can continue for some a big number, but it shouldn't go that so far. We should just stop doing this some point and get every value in each layer, let's say, or in metrics, and consider it as an input to our just fully connected layer. By fully connected, I mean that each and every neuron in each layer in this photo, which is, for example, shown by green color, is connected with every neuron at the next level, which is with red color in this picture, or every pixel in the previous layer, which was the output of our pooling layer, is connected to every layer at the next step, which is green neurons here. So it is a fully connected layer. Okay. This was so far just an introduction what is going on in CNN. So the thing that we are going to do is that we will decide how many layers we will have, and also we will just go through some sample classification task. So let me just share my screen with that one. If anyone have question, you can just jump in and ask your question.
Yeah, there are a few questions in the chat.
Oh, yeah.
Coming from previous. So thank you for explaining nonlinearity, pooling layer, and local features. So Marilyn has a question. So are they basically saying this picture is like this other picture, or more to do with the image in question? Like this part is basically gray and this other section is a different color. I'm not exactly understanding your question, actually. Do you understand?
So they're basically
from
saying this picture is like this other picture.
Oh, for the pooling layers.
Okay. Let me just follow the question.
Yep.
For more to do. Oh, okay. Yeah. If I just get the question, if I just understand question, look, I just provided different examples. No, if we have a gray picture, so we will have just one, for example, one matrix of values. But if we have colored picture, we will have three matrices. So each one for each channel, one for red, one for green, and one for blue. I had provided both gray picture and colored picture. But I'm not sure if it was the question or not.
I always also can add something here. So regarding the first comment by Marilyn, Are they basically saying this picture is like the other picture? Actually, that line of thought, we have a category of methods under contrastive learning that they focus on similarity and dissimilarity of images. But in general, for convolution and convolutional layers, what you do actually for the first layer is to extract some images, as Manizheh mentioned, from the images. This initial features might be about color, texture, edges. And in the next layer, you want to build features on top of these features. So combine these simple features to build more complex and more comprehensive features. And you continue this process. The deeper you go, you are able to actually find interaction and more complex interaction and complex actually functions from these initial features. So you learn features of features of features of features, and at the end, this combination help you to actually learn about object, about the content in that image. So that's in general how they approach it. For convolution, the way that we don't know which number to assign. What we do is we train the model based on backpropagation algorithm and gradient descent that we went through it in the last sessions, and we try to learn it from the data. For each input, we feed that input to the model. Initially, all of these weights might be random, yeah, that we assign, since we don't know what's the ideal value for each filter, for example. But at the end, it gives us a prediction. And this prediction, we know that since we have the input and output, you can find out how off this answer is and calculate the error or loss. And when we have this loss using backpropagation, we try to change the weights of those filters in a way that if we feed the same image to the model make smaller mistakes. So we gradually correct the model to actually be able to learn the concept. And this process is iterative. I think you will see that in the rest of the notebook as well. Thank you.
Yeah. Thank you for adding these comments. Thank you. As I said, for example, maybe for edge detection, we know what to put as the input, but it is not that simple for the next layers. We don't have any idea what to put in that filters or that layers. So we just guess, randomly initialize them randomly. And this is what we mean by learning. We are just going to see how bad or how good was our guesses, and we will correct it through different stages. That is why this learning is an iterative process. I hope it will answer your questions.
Thank you very much, both.
Yeah.
Anay has a follow-up question. He's still a little bit confused about how com2d chooses which number to put in the kernel before pulling the layer. I think, if you want to repeat some of the answers that was said before as well. But yeah, sorry, go ahead.
Oh, yeah. As I told Amy, if I am just spelling correct, as I told, initially they are just random values. We just go through some random values, but we want to correct them. So we just look at the error and just backpropagate that error, and just at the end, we will just reach to a very comprehensive so let's say near optimal values. That is the process.
Thank you. Yeah, these are very good questions. And Anna, the question, what is the benefit of performing multiple weak polling rather than just one strong polling, quote unquote strong? So what's the benefit of doing convolution polling many times?
Okay. I can say that if you just think about it, especially when we say that CNNs are just deep learning algorithms, when it comes with deep learning, maybe it comes to mind that, okay, I will go with many layers and I will learn much, but it is not the case. you cannot have, you will not gain a lot with adding lots of convolutional and pooling layers. At some point, you will see that adding those layers will not add any value to your classification. So you will just stop it. The main point with, I'm not sure what does weak and strong pooling means, because pooling have just one functionality. It reduces the size of the output of convolution layer. But we don't have weak or strong. If the question is which one to choose, either we should average or just choose the maximum. I can say that there is no a good, for example, explanation that we should choose this. This is better than, for example, average is better than maximum, or vice versa. Each one has its own value and its own use. But yeah, we gain something and we just lose something else. With, for example, it will increase our computational time if we do averaging, or the vice versa. But yeah, I think I can say that for.
Yeah, and Anna just made her question a little bit more clear, what she meant by weak versus strong. So she said she meant we went from 8x8, 4x4, 2x2, but why not just 8x8 directly to 2x2?
Oh, okay.
That was what she meant.
Okay. Yeah. Maybe I can say that if you're just jumping from 8x8 to 2x2, you will lose lots of information here. For example, it's in comparison with 2, the difference is not that big. But imagine it was 16x16 to 2x2. So if we are just doing maximum and just choosing maximum values by when we have 8x8, you are choosing between 64 values, but so you are losing lots. You don't want to just lose that much information at the one stage. But as I said, you don't have lots of, you won't need to have lots of pooling and convolutional layers. That won't help a lot. And there are some just in instructions that what is the good values for these for these layers. There some people say it can be 2x2, 4x4, like 8x8, but not too big matrices. I can say that.
Perfect.
Yeah.
I think we don't have any more questions, and we
Yes.
can move on to the Google Colab part.
Oh yeah, let me. Okay, I will go to this. Let me. Okay. You have my screen?
Yep.
Okay, nice. So in this notebook, I have provided the explanations that I brought in the slides. If anyone have missed something, just maybe can understand better if just go through them later. But feel free to ask anytime about the reasons. And also here I have provided maybe a better demonstration of what is CNN doing. Just a quick example, a quick explanation. Look, I have at the just left side, I have a digit, handwritten digit. I want to train my whole my network to learn what this digit looks like, so that if I just provided another type of, for example, my handwriting is different from another person. So I will train the whole idea to the network that, okay, when by letter A, I mean that it should have this shape, something like this. I want to train this network that by A, you should have some features, you should have some patterns in your photo. And this is what these convolutional layers or pooling layers does. You can see that layer by layer, the size of the just filters just goes smaller and smaller, and at the very end we have just flat layers, which is just fully connected layers. You can go through these later and ask questions. I can see that there is maybe a chat. Oh, I'm not sure. This should I share the link for this notebook in the chat, or what can?
Yeah, sure. But I also uploaded it into the Google Drive folder that everyone has. So if you follow this link.
Oh, so if everyone has there, I won't go
Yeah,
through
let's do
that to save the time. Yeah. Oh, okay. So if just you can go through these and understand better what I was maybe saying and miss something. Okay. We will go through coding with PyTorch. You know that in PyTorch we are working with lots of libraries, and it is fantastic. We have very powerful libraries for process, for example, for image processing, for text processing, whatever. So here at the very beginning of coding, we just import those libraries and we will use them. I will not just explain what each library does. But when we just go to some point, we can just get the idea. So at the first part, we have some libraries from PyTorch, and at this later we have some libraries for other reasons. For example, for numerical calculations, for example, image processing, for plotting something, or other reasons. So I will just run this part. But look at here, I will show you the process while we have our data sets from as a library, not our own data set. Later, I will show that, imagine you have your own data. And you want to run your code on your own data, which is the case most of the times. But here, just consider that we are just using a data set from this library, Torch Vision. We have imported data sets. We will just use a data set which is MNIST from this data from this library for, let's say, for now. As you may know, we will have training data and testing data. So as you know that we will just train our network on the training data, and later we want to see that, okay, we have some new photos. And we question that how good is our network working, or does it have acceptable accuracy, let's say. For example, our network has gone through thousands of images, and we think that, okay, it has a good, through the outputs, we assume that, okay, our network have learned the weights. It has the idea what, for example, the letter A looks like. But we want to just feed it with some new data that it haven't seen before in the training stage. And that is what testing data is. We won't feed testing data while we are just training our networks. And at the end of training, we will just feed the test data and to see how our network was doing so far. I will just mention a point here. You know that the learning process is just iterative process. For example, you will see some images one time, then get an error, then you will go back and correct it. And it is not the case that just by seeing just once those images, you will get good results. You will go through them many times. And you will see that every time that you are just iterating, your accuracy is going better and better. But from some point, you will see that no, it is not that case. For example, if you just consider the accuracy of your classification, you will see that no, it doesn't. When we just iterated more, it doesn't do good. And vice versa, it just gets worse on your data. I assume that you know this. You should stop training on your training data at some point. And we have some methods to decide when to stop learning. Anyway, so we just feed the training data for our training purposes, and then at the end, we will see how it works on the testing data. Okay, by running this part of code, you can see that it says that, okay, I rerun that and it disappeared, but you can see that our data is downloaded successfully. Look here, even here, for the training data, the train value is true, but for the test data, the train value is false. That means that we are not going to use it in the training part of our process. Okay, this part of code just is for demonstration. I have just chosen one digit. For example, I wanted to see the tens image in my data set. I can change it to, for example, 15 to see what it looks like. Okay, here. And it is a different digit. For example, maybe it is 7. The network will learn how to classify this as digit 7. And you can see that this is a gray image, so we will have just one channel. Our input image is a gray one. But if we had something like a colored image, we should have 3 layers of this image, one for red, one for green, and one for blue. Okay, let's just pass this part. Oh, yeah. And in this part, you know that when we do processes, so far we have been using CPUs, but with deep learning, we will need GPUs. We need more strong processing units. In this here, we will just check if Google Colab can provide us with GPU. We say that, okay, if any GPU is available, please assign it to our working space, just that. Okay, and here in this part, we have downloaded our images, but we should change it into some format that we can work with it. And also, we will just divide it to some, let's say, batches. By batches, we mean that, look, for example, imagine that we have thousands of images. We want to train on that. We can say that, okay, when I feed one photo, I want to get error and back propagate that error to just correct my initial guesses on the weights. I can do that. But the other way is that I will not do one by one. I will do, for example, 100 by 100 photos. So what can I say? I can say that, okay, I will see 100 photos. I will just postpone my back propagation and then apply that propagation. I will keep those values, for example, error values, whatever, and then I will apply each training step after, for example, 100 of images, not by one by one, sorry. And so that is the idea behind the batch sizes. But I assume that you have heard about this in the previous stages, so I will not go through that. And also, I can say that I want, this is a deep learning task, so I want to just get more powers from my working space. So I will say that if you can provide me more powers, not don't do it in a sequential form, do it in parallel form. The number of workers and just do that. It denotes the number of processes that generates batches in parallel. It can be get the value 1, 2, but here let's say we will do this. So it changes our downloaded images to some format that our model can use that. And it is stored in here in loader. You can go through the documentation for data loader of Torch, and it has lots of parameters to set. Let's here I have just provided 3. Also with shuffle, we mean that you can for the input data will be shuffled. So it is not the case that, for example, first 100 photos are devoted to digit 1. The second 100 is for 2. No, we want to just shuffle them and not to just provide better unbiased data for our training. So the shuffle parameter is true for both training and testing data. Okay, so far we have just downloaded our data and changed it to a format that our network can use it. But our main part is to decide what is the architecture of our network. So how many layers it will have, how many convolutional layers, how many pooling layers it will have. If you just look at here, we have a class here, and the name is ContNet, which means that I will just I will have a class with the name ContNet, and I will initialize an object of that, which is a neural network. From your previous studies, you know that here we just mentioned the structure, and if we not initialize an object from this class, we won't have the real, I mean, a network, a real network of this, an instance of this class. So here at the first part, it is just some definitions. For example, with conv1, I mean that whenever I'm just using conv conv1, it is a convolutional layer, and the input channel is 1. Let's just read this, and I will just explain these values. But okay, the input channel is 1, the output channel is 16, the kernel size is 3, the stride is 1, and the padding is 2. Okay, let's see what these values mean. Previously you saw our picture that was a gray one. So as I told you, we have just one channel for the first layer. I will give it just 1 because I have just one channel. But later, I will feed it to a network which it has 16 channels. Just go back. Okay, so if I have 16 of these, I will, in the training phase, in the training stage, I should learn what each of these layers should look will be. So I will feed it to 16. Sorry. Okay. Yeah, the input channel is 1, but I will say that it will be changed to 16 layers. And by kernel size, you remember that I showed you, I told you filter, and that is what we are going to learn, yeah? So it means that it is a matrix 3 by 3. So the kernel size will be 3. We had that number here. Look here. The input image was 6 by 6, and the filter was 3 by 3, and the output is 4 by 4. So by kernel size, we just specify the size of this matrix, which is called filter in CNN. So that number shows that is 3. And by stride, look, I said that this matrix, okay, we multiply it at these 9 values, which is all 10. Then we move it one cell to the left, to the right, and then repeat these calculations. If we just decide to move it not by 1 by 1, by 2, but by 2 by 2 columns each time, so we can set this value here. We will say that, okay, you can go 1 by 1 or 2 by 2. So it is up to us to decide what to do. But here, let's say I will keep it at 1. And the next one, padding. Look here. I told that I will multiply it, this matrix, this filter, to the first 9 cells here. So if we just move this filter one column to the right, it means that I have considered the first 10, the leftmost column just once in our calculations. And I won't see them again, even if they just have some useful values, but I will just calculate these values just once, and it is not good. So by padding, I will say that okay, let's just add some 0 values to the left side of this matrix. If padding is 2, So I will add 2 0 columns to the left side and 2 rows to the upper side, and also to every side of this matrix, so that this the values in the leftmost or rightmost or upper or bottom side, they will be calculated, they will be counted as the number, for example, as the same as the values in the, for example, in the middle of these matrices. I can see that there is some question in chat. I will go through if it just. Okay, no, it doesn't. Okay, sorry. Yeah, whenever it was not clear, just jump in and ask your questions, please. So by padding, we mean that. So we add some 0 values. They shouldn't affect our outcome, but it will help us to treat equally every value in this matrix. Okay. So by padding, we mean that. Here padding is 2. So we will do this. This conv1 is just specified in this way. But for example, for conv2, it is different. It can be different. And also for other, just you can see here, we have nnn.conv2d for specifying what our convolutional layers can do. Okay. I can see a question in the chatting room. Let's I will continue, and if you don't get your answer, I will just answer your questions. Okay. So here we just introduce or specify how many input channels our convolutional layer has, how many output channels, what is the kernel size, what is the stride value, what is the padding values. Okay, here we just initialize the values. And also we have another, let's say, we didn't speak about this in the slides, even I was explaining the convolutional layer. This is just, let's say we have another layer, which is a batch normalization layer, that we just normalize the values on the layers, just not to have very large, very small values. So just, and its size is just as the size of our output channel of the previous convolutional layer. So just keep in mind that we do normalization on the values. And here in this nn.relu, this is our activation functions. As I told you, I just showed you, there are lots of other activation functions. For each application, you may choose different activation functions. Here we choose relu, but you can just go through to documentation which type of activation function is suitable for your application, and you can choose that. There are good documentation in this regard. Look, here we are just initializing the values. It doesn't mean that our network will have conv1, then relu1, then conv2, relu2, and something like that. This will be specified in our other function here, which is named as forward. It's just, we are just saying that, okay, the structure of when conv1 is this, the structure of pool is this, structure of conv2 is this, and like that. So Just you can just change the order of these values here. It doesn't matter. But later it matters which one to put which one where. Okay, so I won't go through each and every row here. Just I can say that, okay, by CON1 I have input channel 1, output 16. By convolutional layer I have input channel 16, then 32. And by convolutional 3, I have input 64, then I will have 32 and something like that. I can specify what the values here, but I will, I should keep something in mind, that my input channel, if I am dealing with gray pictures, it should be 1, and it is colored, it should be 3, and at the end, I will have a fully connected layer, and the output features of that should be the number of classes. For example, if I have, I am just going to classify between the digits, so I will have 10 classes, one for each digit, 0, 1, 2 to 9. So the number of classes will be 10. Or if I have a classification task between, for example, I am just classifying pictures if it is flower or not. So the number of classes is 2. So I will just specify, put a number 2 here, or the other values also. Okay. So here, after we have just make our decisions that what is the values here, we can now decide which layer where. As I told you, the order of these specifications can be flipped here, but here we are just specifying which layer first, then which layer. And I forget to say that here, look, I have just one definition for pooling layer, and it is max pooling layer. Maybe you have just you were thinking that we should have, for example, pool 1, pool 2. No, I just need to have my pooling as max pooling, and its size will be 2, which means that I will go through the photo, the pixels 2 by 2, for example. This is the output of my convolutional layer, okay? And I will just consider a matrix which is the size 2 by 2, if I just specified there 2, and I will get the maximum value of here. If it was average, I was doing averaging between those 4 values. Whatever that number is, I will consider a matrix. For example, it was 2, I will consider a matrix 2 by 2. If it was 3, I will consider it 3 by 3. But I have decided that, okay, for each layer, I will just keep it fixed at 2 by 2. So I had just one definition for my pooling layer. Just it was named pool, not pool 1, pool 2, and so on. Okay, I think I have run this part of my code. Then I will, by running this, I'm just saying that, okay, I have this kind of this structure for my network. Let me just check the chatting room. Okay, thank you, Dr. Maliki, for answering in the chatting room. Thank you. Okay, I will go through this. Here, we have just specified what is the we have specified our class. We named it as convnet, and we should just initialize it. We should say that, okay, I have an instance of this class, and this is where our model is. Our model is made. This in this piece of code, we will say that, okay, I have a convolutional layer. Let's say that, okay, we were just going to decide what is the number of, what is the digits 0, 1, 2 till 9. So we had 10 classes. We will specify it to 10. And just we were just checking if there is any GPU available. We will use that, and this is that part. And if we just print our model, it will say that exactly what each layer has. So you can print your model anywhere in your code. No need to just go back to see what is your network looks like. And also you can see the number of the numbers. For example, for here, our input features was just like by flattening, by just concatenating the values at the very last layer of our convolution. Here, if we just put every pixel side by side to just make it one two-dimensional vector, 1 to some number, then for our network that just we decided which numbers should be here, we can here see that our fully connected layer will have 1568 values. This is very small value in comparison with if we just going to from the beginning fully connected layer. It is a really small value you can see here now. Okay, so far we have decided what is the structure of layers, how many layers we have. Oh, I will just go back and say that, okay, look, we have, we have one convolutional layer, then our relu function, activation function on that, then a pooling layer, then another convolution layer, then batch norm, as I told, it is just normalization on the values, relu, and pooling layers. So I have decided that my network will have just 2 layers, not 3, not more. So you can just add to these values. For example, you can just go, for example, my output is some something like conv. For example, if I had 3, I'm not sure. Yeah, I do have conv 3, then it will be applied on the output, which is the output here. You know, you can see that it is sequential. The output here will be the input for the next layer. This is layer by layer. So I can just specify the convolutional layer, then I should say that, okay, for this layer, what is the for example, activation function, what is the pooling, do I have a pooling layer or not? So I will just delete this, but you can here you can decide how many layers you will have, and this part will just specify just the last layer that we had. Okay, so we do have our architecture. It is ready, our network is ready. We should go and train our network on that. So let let's say I will go fast because I'm going to just short of time. But here you have an idea what is the number of epochs. I mean that how many times I'm going through those my training data. I have just selected a small value. It shouldn't be like this. It should be, for example, some value, for example, 20, 30, but you should have, as I told you, you cannot give it a big number. It will be waste of time, or even it will make your network worse. So there are techniques to just decide when to stop training. Here, for a short of time, I just select just a small value like 3. This part here, I will I'm defining what will be the training. By training, I told a lot. So it says that, okay, you have some model, you have decided what the number of epochs, how many times it will go, and you have the data. And inside this this part, which is a definition, you will decide what will be done while training. So here we have 2 4 loops. It goes, for example, for the number of epochs, it goes through all the images in our training data, and it will just feed your input, your data, which is images, to our network, which is an instance of our network, and we get the output. Okay, it is just goes forward loop. But what about learning? We should have some backward, and for that, just we have gone through the network. We should have some functions, something based on which we say that, okay, it was doing good, doing bad. So that is what our loss function does. We should just here we have said that, okay, I will consider cross entropy loss as my loss function. I will explain this more if I had time at the very end, but look, we are doing somehow optimization, and we are just minimizing our errors. So we are doing optimization, and for optimization we should have some function to just make it based on that. We will decide, are we doing good or bad? And this is where this is one type of function we can do, or we can do maximization. But here, if we just decide to maximize, we shouldn't maximize our loss, we should maximize our accuracy. So based on our function, our optimization will be different. There are other functions for this part as well. You can go through that. I won't explain much of this. But anyway, so whenever you just feed your images and get the output, you will provide it to your loss function. And here there is a comparison between what is my network gave me output here and what are the real values by here. So based on these, it will calculate the loss value. And just skip this part, which is just it will clear gradients. Just skip that. If I had time, I will go through that. Oh, okay. Here we get some loss values. We want to just use that loss value to go to train our network, to say that, okay, this layer had this just have this extent of error, to better say that. Okay, I have, for example, my error value was 20. The part of first layer from this 20 was, for example, 5. The second layer was, for example, 4, something like that, or whatever. So I will go back in my network, and based on loss function, I will just correct my initial guesses. So I will do this iteratively. And also this part, okay, I get the loss, I just go back. So let's apply those changes and something like that. Okay, I will, so it will go through each and every image here and train our network. If I just run this, which will take a bit long. Okay, look here, we have defined our functions, so we need to just call it with the number of epochs and the model that we have created before and our data, and each iteration it will provide me some values. Remember that when we were just at the beginning, we were just loading and explaining our data here. We told that, okay, you should go 100 by 100 photos. That is why in the output, you can see that, okay, this is, I'm going 100 first, then 200, 300, and so on. And it will go through, I just put number 3 for epochs. This is the epoch values for epoch 1. And you can see that the loss is just going to be better and better, but somehow, for example, here, it just goes up. It is normal. It will fluctuate there, and it is normal, but it learns. The other epoch, overall, the loss value will be lower than the first epoch. It is supposed to do that. We expect that it goes better and better by epoch, and that will be the process. It means that it is learning and our error is just reducing. Here we are just the network just goes through the input, the output, error, then that back propagates that. Let's wait for that to see how far it will go. If, for example, 3 is a very small value in this for this task. 3 is just very small value, so our losses doesn't go very to very small values. But when you have time, you can choose large numbers for your number of epochs. Anyway, it is going to be better. It is running. As it is running, I will go to the testing part to just save my time. Here, just if you have a quick look here, you will see that there is no training here. It is just one direction. We will just feed our data, which is our testing data, to our network, then get the predicted values, and from that we can calculate either our loss value or our accuracy value. Here I have shown the accuracy value. Oh, it seems that the learning have just finished. So you can see that at epoch 3, we have this value here. Of course, we have other values in epoch 3, which are these rows, but it means that it is going to be better and better, and that is the thing we were just expecting. Okay, after our network was trained, we will feed our testing data, which our network haven't seen in the training phase. And this is the testing part, which I just consider accuracy as to see what is the accuracy. Oh, it is good. It says that 98% of the times our network was guessing good. So it is good. I won't go to the details, but feel free to ask every time you have questions. I will just go through the chat to see if I am missing something here or not. Oh, Anna, I can see that. Look, we will continue our training on our network for some iterations, and the output of that, then we stop training, and now we have those values in our filters, and we will use those values for our testing. We don't just keep the values from the beginning. Every time we update our values, and at the end, our network will have weight. And it doesn't. We can't say that, okay, just keep the values for epoch number, for example, 3 from step 2 from 6. We cannot say that. At the end, we stop training at some point, and that is our network. But yeah, you can save the model and then use it for your later testing purposes. Okay, it is done for now, but Dr. Maliki, do I have time just quick showing how, this was the data set from the library, if what we can do if we have our own data, or if it is covered in previous.
Yeah, you have time, feel free.
Yeah, thank you. But anyway, if anyone have some problem, just please ask. Okay, I will, this was just, you remember, we had our data from this library that we imported. So what we can do if we have our own data, okay, so I will just show you here. Actually, I can provide this to the students too. Here, I have decided that I will go through my own data. So I need to save my data somewhere. With Google Colab, we can store our data in Google Drive. So I just have my Google Drive. Then upload my drive there. Let me just, sorry, get rid of this. For example, yeah, my drive here. I just add new here. I will upload my folder which contains my files to the Google Drive, and then here I can say Google Colab that please import or mount my data from my Google Drive. You can just choose whatever name here. For example, you can write data, whatever here by let me just do this. And by doing this, and if you just go through your files, you can see your data there. It says that just download just mount whatever is there in my Google Drive to G Drive. So I will go this part, Then I will go to my drive, which is the same, will be the same for yours too. And later you will, I have provided a data set named brain tumor classification data set, and I can find it here. And it has some subfolders, training folders, testing folder, and each one of these also contains some images, which is in format .jpg. So that is how you can import your own data for your Google Colab environment. Yeah, and I will just get rid of this. Yeah, and if you run this, it will say that, okay, if it was not in my drive, it will just go through the I mean my Google Drive and mount the whatever file is there to my here to files, and here I can see that what is there. It says that you have 2 folders, G Drive and sample data, but my data is in G Drive. If I just go and say that, okay, let me just here go and date that, okay, CD G Drive, okay, and run this and just and say that. Oops. Okay, let's try other way. I will say that, okay, my G Drive, then my drive, sorry, just content that G Drive. Okay, let me just go back and do this. Oh yeah, because I have done this, it says that I can see just your my drive, and I can just get rid of this error. I should just restart my Google Colab, because I told it just go to this part and it will just go to say that there is no directory because I was already there. So I will not go further, but you can just go to my drive, then your folder, and like that, and you can see what is there. Whatever if I just specify the terrain path, the testing path here, I will get access to my data there, and the process, of course, will be different. For example, data loading, data splitting your data to test and training, whatever will be different here, because our data was different, our processing was different. If anyone was interested, maybe you yourself can just find the MNIST data from the internet, load to your just upload it to your Google Drive, and just go through the same process that we went with the previous codes that we have, and to see if it works or not. It can be a good practice for you. Yeah, I think this is all for me. And I was going to say something from our previous here. Yeah. Yes. Look, see, here I just specified my third convolutional layer. I didn't use that in my network. If I was going to use that, I should be specific about the numbers here, because the input channel here should be 32, which is the same as the output of the previous one. And it can be something like 64 here. And one thing that nobody maybe was mentioning is that I did mistake here with the number of classes, which was 4 by mistake. It should be 10, but anyway, because I was not I will when I was just initializing, I told that number of classes is 10, but there should be consistencies here too as well. Yeah, that is all from me. I can I'm waiting for questions if anyone has.
Thank you so much. So
Yeah.
everyone, if you have any question, feel free to either add it to the chat or you can unmute and ask as well. So I think students asking if they can get access to the 2 more data sets.
Oh,
Public data sets?
oh yes, I can share them.
Perfect.
I can share them
Yeah,
with you.
if you
Then
share it with us, we will
Hmm.
share it with the audience through the Google Drive. And
Oh
you'll
yeah.
find out on the, perhaps we share the information on Discord channel as well.
Oh yeah. Yeah, of course. I will do. Yeah.
So do we have any more questions? Let's see. We had a question about will the model use the last iteration, which does not have the lowest loss value in this case? And Farhan already answered, but feel free to add to it about saving models iteratively.
Yes, as Dr. Malik said, we can save the model, and it will be the last, the output of our last training model, and we can use that.
Andrew had a question. You mentioned that if we had more time, we could do more epochs. How many are normally used, and when there is less time constraint?
Yeah. What I do is that not I do normally we choose it at a number, for example 30, 40, sometimes 100, whatever, and we just check our training and validation I mean accuracies or loss. If we are just considering loss values on training, it will go down and down, but on validation data, from some point it will go up and up. I can say that we maybe you have heard about cross-validation. By cross-validation, we mean that, for example, we have just ignore the testing data. We won't do anything on that, okay? But on the training data can be will be divided into 2 parts: training and validation data. On training, we will train the data, but on validation, we will just report the error. But that validation data will be used in the training cycle, just opposite to testing data, which we will not see in the training phase. So we will decide on the output of the validation data. If I'm not sure if I can draw a picture here. I haven't.
Yeah, I think Zoom has a whiteboard. You can click on the whiteboard.
Let me try that. I can find. Oh yeah, it has whiteboard. Yeah. For example, let's say that you have this diagram. If you just check your just training accuracy or train, for example, you are considering error. If you just consider a training error, it will be like this, epoch by epoch. But if you just consider validation error too, you will see that it will go down, and at some point it tends to go up. And this is the place where you can just stop training. And this is just one way of deciding what is the best time to just do this. I will stop this. I'm not sure. Sorry. Yeah, I hope I could answer that question somehow. But was it clear?
Yeah.
Okay.
And I guess a follow. So that was pretty clear. I guess a follow-up question would be, how would you decide that prior to training the model, or would you decide that as you're training the model when to stop? And if you can explain early stopping a little bit.
Pardon, I didn't get you.
Oh, can you hear me better now?
Oh yeah, yeah. Do please
Yeah,
repeat.
yeah. I was saying, I guess a follow-up question is, how would you, do you get that optimal stopping point before training or during training or after training? And would you like to explain early stopping a little bit?
Oh yeah, as I told, what I usually do is just select a number, for example, 50 somehow. Then I just check the validation error. Whenever I see that, oh, it is going up and up, it means that, okay, my model is overfitting. I didn't just mention that, just skip some just extra points, but by overfitting, it means that when we just go lots of epochs, our network will just memorize what the photos looks like, and it will not learn. It will be just specific to that data set. It will not, and it will not perform well in the testing data set. That is why we use validation error to decide when to stop our training. Otherwise, our network, we will just face with overfitting problem.
Okay, thank you very much.
Thank you.
Do we have more questions coming up? Farad, is there anything else that you would like to add?
No, just a reminder for everyone that we'll have tutorial sessions that cover some of these concepts. Some of you might need some time to go through the slides on your own and perhaps come back with questions. So you will find out the schedule for that on the Zoom, on the Discord channel.
Yeah, perfect. Thank you very much. And thank you very much again, Manizheh, for your wonderful lecture today. And
thank you,
everyone else for coming. We'll return tomorrow for transfer learning, which Sebastian is going to talk. Thank you.
Thank you so much. Thank you.
All right, have a good rest of the weekend. Bye-bye.